I'm starting to build the output module for Ben Eater's 8-bit breadboard computer project. The output is depicted here in the photo. It's 4 7-segment displays. A blank one first that could hold a minus sign if it was a negative number, and then 3 displays for values up to 255, which is our maximum possible output from this computer. Without this display, the only way of displaying results from the computer's calculations would be with using LEDs like here to represent a binary value. But with this display, we'll convert the binary value to decimal and display it this way. So these little 7-segment displays that we're going to be using have 10 pins, okay? And so, 7 segments, why 10 pins? Okay, well, first of all, you have the 7 segments which form the digit, and they're conventionally labeled A, B, C, D, E, F, and G. So you have those, but then you also have the decimal point. There's another LED for that. So that brings you up to 8. And then the other 2 pins are both connected together, and they are connected to the cathodes of all of the LEDs, the side of the LED that goes to ground or to the negative terminal of a battery. Okay, and so it's called a common cathode 7-segment display. They also make common anode 7-segment displays, but that's not what this is. Okay, so both pin 3 in front here, which the way that we number these pins, starting in the lower left corner, pins 1, 2, 3, 4, 5, then going counterclockwise, 6, 7, 8, 9, 10 up on the top. The middle pin 3 down here, and the middle pin 8 up here. Both go to ground, so you can use either one you want, whichever is convenient. I use the top one and connect it through a current limiting 330 ohm resistor here to ground. Okay, and the setup here is that I have a battery attached to the breadboard, and the power rails connected together here, so that I can get my 5 volts down here and put it in any of those pins that I want to, carefully avoiding the ground pin so I don't short out my battery, make a big spark. So that's my task here, is to determine which pin is associated with which of the segments A, B, C, D, E, F, G, and decimal point, for purposes of programming an EEPROM to output decimal values when binary values are put into it. We'll talk more about that in a bit. But so right now I got to identify which pin goes with which segment of the display. So let's just make sure that the battery's turned on. It's a smart battery. It's a little too smart for me. It's intended for charging other batteries in cell phones and cameras, and so if there's not very much of a current draw on it, it turns itself off so that it's not overcharging your battery. Okay, and so it'll turn off on me while I'm doing this probably. But so turn it on first, and then I'm going to apply 5 volts to pin number 1 here, and okay, that lights up this segment, which is segment E. So that's pin number 1. And I'll just record that here. Okay. Then let's try a different one. Let's try pin number 2. There, we're stuck in pin number 2. That's the bottom segment. That's segment D. That's pin number 2. And so on. I won't bore you with the rest of the process here, but I'll continue it and then off camera and then return. So we finished determining which of the 10 pins from the 7-segment display connect to which of the LED segments, making up a digit plus a decimal point. Next, we have to program our EEPROM with this information in mind. And we're programming it with Arduino Nano. All of the green wires here are connecting to the 11 different address pins. This thing has 2048 memory addresses. That's 2 to the 11th power. That's why it has 11 address pins. And then it has 8 input and output pins, and those are connected to the yellow wires here. And what the Arduino is going to do is go through those 2048 addresses and write values, 8-digit binary values, or up to that many in each of those memory slots. The way that we're setting this up, I have displayed up here. We have our LED segments DP for decimal point, and then A through G. And for the number 0, which is in red off to the left there, if we want to display the number 0, we need to have segments A through F illuminated, but not G and not the decimal point. G is the middle segment. In here, we don't want that lit up for a 0. We just want the outline of the circle there, which is segments A, B, C, D, E, and F, and so those are all 1s. And so we're going to store this value, the Arduino will, in address 0 in the EEPROM. And the way we'll enter it is as its hexadecimal equivalent, 7E. And then for 1, we only want to illuminate the segments on the right-hand edge here, B and C. And so this is the binary value 00110000 that we will want to enter in address number 1 to stand for the way to show the binary value 1 in decimal with a 7-segment display. And that we will enter with hexadecimal value 30. And so you can see up here this data array contains these values that we want: 7E, 30, 6D, all these values that we have here for the digits 0 through 9. And that's all we're going to do in this case, because one LED 7-segment display can only show a single digit, and so either digit 0 or up through digit 9. So that's what we're going to do in terms of programming. We have the Arduino connected to the laptop here, and so what we will do now is, if we can find our cursor, we will compile, keep our fingers crossed, and upload to the Arduino. And it says it's compiling the sketch and uploading it, and done uploading. So okay, we'll open up the serial monitor here and see what's going on. First, it's going to erase the EEPROM by writing 1s everywhere in all 2048 memory addresses. It's going to write 8 1s in each of those locations to erase the EEPROM. And then it's going to overwrite some of those first few values with the ones that we're putting in for the digits 0 through 9. So there it's done, and showing us and reading what's in the EEPROM now, mostly 1s, and then here up in the top row here we have 7E, 30, 6D, all these values that that correspond to the digits 0 through 9. They're writing a few other things in there that we'll talk about later, but that's the important part of it. So what's left to do now is to pop the EEPROM out of the programmer here and wire it up to a 7-segment display, and then test to see if we can indeed have binary inputs for 0 through 9 and decimal outputs. So that's coming up. Okay, we have the EEPROM wired up to a 7-segment display. All of these wires down here are connecting the output pins of the EEPROM to the input pins of the 7-segment display, and that's based on what we found out going through the pins of the 7-segment display to see which pin was hooked to which segment. The output pins of the EEPROM are 9, 10, 11, 13, 14, 15, 16, and 17. And if you put a 8-bit binary value into a memory address, the 8-bit value will come out with the least significant digit coming out of pin 9, the next to the least coming out at pin 10, and the most significant digit up here at pin 17. So we've got those associated with the segments of the display, so that we connect these wires together. Pin 17 of the EEPROM connects to pin 5 of the display, and so on. So that, for example, if we have a value in memory at some particular address, let's say at address 0, we have a 0 stored for the most significant digit, then all ones until you get to G, and a 0 there, then that's going to, if that value is output to the 7-segment display, it's going to light up everything except for the decimal point and the segment G. Okay, so it'll light up 0, not G and not the decimal point, and that's decimal way of representing the value 0. When we get to 9, the value for 9, we're going to want to have values stored here in the 9th address in the EEPROM that will light up the segments forming the number 9, and everything else zeros. So that's what I hope that we have done here. Hopefully I've got this wiring correct and corresponds to what we had written down here. The other jumpers here are all connected to the address pins. The EEPROM has 2048 addresses for memories. Each of those memories can hold 8 bits. The 2048, that's 2 to the 11th power, and that's why there are 11 of these jumpers here, one for each address, and we're treating this as the least significant bit of that 11-bit binary number, and then up at the top up here somewhere we have the most significant bit. But all we're interested in really are these 8 bits down here, these 8 address bits, and in particular, since this display can only show 10 different digits, we're going to be satisfied with these 4 bits right here, which correspond to 1, 2, 4, and 8, and with those we can make up the digits 0 through 9. And we just hope that we'll be able to get the appropriate decimal display out of here when we set the binary input correctly with these 4 jumpers. Okay, right now everything is set to 0. We need everything tied to either 0 or 1 so the pins aren't floating, just so that we don't have LED segments that are flickering or something. So everything is going to be tied to either 0 or 1. Right now everything's tied to 0, to ground. And plugged into our battery, turn our battery on, and hopefully, yes, we have 0 being displayed here. That's good. So we'll change our binary input, which is going into the address pins. Let's say we'll change it to 1. 0, 0, 0, 0, 0, 0, 1. And yep, we're lighting up the appropriate segments for 1. Let's try doing 0, 1, 0, 0, which is 2. And yep, we're getting 2 as our output. Let's make it 0, 0, 1, 1. That should give us 3. Yep, binary 0, 0, 1, 1 is 3. And so on. Let's try going up to the point where we are putting in 1 0 0 1. Okay, 1 0 0 1. Oh, our battery's gone off. Turn it on, and sure enough, that's 9. 1 0 0 1 is 9 in binary. And of course, I'm omitting to mention all the leading zeros for a 11-bit, 11-digit binary number. But it looks like we've got this thing working. So the next step is to add more 7-segment displays. And what we're going to do to avoid having to use multiple EEPROMs, we're going to do some multiplexing. And that's going to involve building a clock out of a 555 timer, and then also a counter, 0 to 3 counter, a 2-bit counter here, and we'll talk about how that can be used to produce values up to 255 with a total of 4 7-segment displays here, also allowing for negative values down to negative 127. So that's for next time.